Next up, Leigh Orf will be talking about unlocking the mystery of the most violent tornadoes.
Okay, all right. Thank you, everyone. And so I'm going to talk today about tornadoes and data compression, and I'll let you decide which is the more exciting thing. So I wanted to acknowledge my collaborators. Kathy Finley is co-PI in the PRAC. Bruce Lee is one of our collaborators, and Robert Wilhelmsen, you may know, was one of the pioneers of three-dimensional cloud modeling, who's also involved in this work. So I'll talk about what our research goals are, why this matters, why we're using the machine, specifically talk about the results from a specific environment that we've been simulating, and then I'm going to sort of switch gears and talk about some floating point, a lossy floating point compression algorithm that's now available on Blue Waters that works with HDF5 that is sort of opening the door to doing some extra things that I never really imagined I could do, and then I'll just wrap up. So our research goals, we wish to simulate thunderstorm phenomena, in this case supercells that produce tornadoes, at the highest resolution we can for some of the same reasons that Ryan just mentioned and Don about, as you get to higher and higher resolution, you start explicitly resolving features that are very important. And with supercells, we're interested in what's going on near the ground with tornadoes and tornadogenesis, maintenance, etc. And I'm also very much a proponent of visualizing, not just because it looks good, but because doing three-dimensional volume rendering and trajectory clouds and things like that helps us to decide where we're going to go quantitatively into the data. And finally, the overarching goal, which is that of much of the mesoscale meteorology, is to understand the internal workings of supercell thunderstorms well enough to significantly improve our forecasting of their behavior. We're currently unable to really forecast whether a supercell is going to produce a tornado with any real skill. So why study these top-end storms? EF4 and EF5, those are the top two categories of what's called the enhanced Fujita scale. The EF5 is the top category, so those are winds perhaps up to 300 miles an hour near the ground. The long path tornadoes, for obvious reasons, have the potential to do the most damage, and despite lots of very good work in the field and modeling work, we still don't know why some supercells produce tornadoes, weak tornadoes, or no tornado. And we really want to have the ability to discern these things for the forecasting problem to get people out of the way. So what do we need to get this to work? A good model. We're using CM1, developed at NCAR. It's about 10,000 lines of Fortran. George Bryan wrote the model, and it does overlap communication with calculation, so it's pretty efficient at scale as well. We need a good set of initial conditions. In this case, we went to a rapid update cycle forecast model. We plucked out a vertical sounding from a 1-hour forecast that was adjacent to an actual storm that formed and used that as the initial base state for CM1. We need good hardware. Well, we got Blue Waters, so that one's taken care of. And on the software side, I've been using Visit and Vapor for visualization and an awful lot of my own custom code that I wrote in order to manage data, and I'll be talking more about that as I go along here. And you need a bit of luck because if you're a storm chaser going out to chase storms, sometimes you see a supercell doesn't produce a tornado. When you're a numerical modeler and you simulate a supercell, sometimes you don't produce a tornado. So if you're really trying to study the top-end storms, you don't know what you're going to get before you run the model. So why Blue Waters? The scale of the problem just demands it. When you double the resolution, it takes 16 times more computation. It's a very steep curve. Just to give you an idea of the size of the problem, the 30-meter resolution simulation I'll be talking about, it's about 2 billion grid points. We've done some simulations at 20 meters and even higher. That's getting up to about 8 billion grid points. Now you're on like about a quarter of the machine. We've created, as far as data is concerned, I would say about 3 petabytes of data over the years. Back of the envelope, we've got about half a petabyte of data that does contain high-end tornadoes in it. Key challenges, just getting the storm to form that produced the long-track tornado. Just like the talk on the plenary talk about how you can't reproduce your results sometimes, we found that the sensitivity to initial conditions and model parameters is extremely high. When I go back to rerun a simulation and I do a small adjustment, say, of the model domain, so the storm stays in the center of the box, sometimes the tornado doesn't form. So we have these horrible, they're kind of horrible from a forecasting perspective. They're fascinating from a scientific perspective, because if you can have two simulations that are virtually identical and one produces a tornado and one doesn't, there's some interesting things to learn about why the one didn't. Handling the data load, we need to save data very frequently, about once every model second and even higher, to study what's going on in the tornado. I've spent more time in the past decade wrestling with data than I have doing science, tornado science. That's changing because most of the bigger problems have been worked out. And visualizing data in a way that elucidates important structure and allows comparisons to observations, because that's extremely important. Brief shout out to Rob Cisneros and Garrett Haber, folks who've helped me along the way with both volume rendering. Rob helped me with the Visit plugin, and Garrett has helped me with some HDF things, and the help is always useful. And again, a big thanks to all the Blue Water staff. Without you guys, it's just a big pile of silicon and copper. So as far as accomplishments go, we've got a few articles out. One major article, Cadence documentary, has been includes some of our simulations. We've had a lot of PR since the university put a press release out, and it's been good. And we got some graduate students coming to join my research team at the University of Wisconsin. I'm very happy about that. So overview of the simulation. So soon I will show you a very long animation of one of the storms we're studying. So we have an EF5 strength tornado that exists for 1 to 2 hours, and I say 1 to 2 because it depends on the exact simulation we're doing. One common feature in just about all these simulations is we have non-tornadic vortices that precede the tornado that seem to provide vorticity to the tornado to help it form and also to maintain it. This occurs along the boundary between the storm's cold pool and the environment ahead of it. We see these accumulation processes. These are things that you would never be able to see at lower resolution. Just like you can't get the sea surface temperatures right with your hurricane if you don't have the high ocean resolution, just like the previous talk. The same thing. These are things that we just never would see before because we didn't have the computational abilities to simulate it. We also have identified a feature we call the streamwise vorticity current that seems to be very important in maintaining the storm. So here's a volume rendered image of the storm showing you the size of the model domain, also giving you a sense of scale. There is a tornado there. I'll let you see it. There it is now. But we really have to run the main simulation over that entire domain that you're seeing at 30-meter isotropic grid spacing. We do stretching on the lateral boundaries and at the top, but this is all 30-meter grid spacing. And there's a tail cloud, and a tornado, and a wall cloud. Okay, so I'll let this go in a second. So this is cloud, this is rain, this is buoyancy at the surface, this is also buoyancy at the surface, but this is north is here, we're looking towards the west in the three-dimensional image. This is radar reflectivity at 1 kilometer and 1 kilometer updraft. And I'd ask you to focus your eyes on this region here in the updraft especially, because we're looking for precursors to the tornado formation. And one precursor that I see here is a strengthening in the updraft at 1 kilometer. You'll notice when these reds start to get really dark. And so that's one thing to keep your eye on. You'll notice this is the forward flank of the storm. You're starting to see certainly some transport of something. You see these little cloud tags here. These are actually representing these little vortices that I've been talking about. You can sometimes see them in the cloud field. But now look at your updraft. It's really strong. It's sort of gotten wider. Things are like smoother, and you'll see that in some other imagery as well. And then you see the condensation funnel comes to the ground. By the way, the tornado was actually in existence before you saw that in the vorticity field. That's another good result. Tornadoes, you can have a tornado without having a condensation funnel. And you do have tornadic winds at the ground level before you see that. But there's a lot of interesting things going on here. The tornado is a 2-cell tornado, so you see that blue bullseye there. That's the downdraft in the center of a tornado, so that's an easy way to track its location. One of the reasons I like this particular simulation is that out of sheer luck basically, it looks like this thing's just planted on the ground, but we're actually moving with the storm at almost exactly perfect speed. So the tornado really doesn't move around too much from a box perspective. What that means is I can save less data and just focus on the tornado without having to chase it around the domain. And as I'm talking, this thing is creating winds of 300 miles an hour near the surface. You're seeing pulses in the rear flank of the storm. But really most of the interesting things seems to be happening along the forward flank, which is this region here. It looks like everything's going down the drain almost, and it's really going up the drain because the tornado's pulling it all up. But it just goes on. Now it looks like a nice wedge tornado. I don't know, all the storm chasers have different terminology, but it looks very realistic. You're seeing subvortices within the tornado itself. One issue that remains, we have to get centrifuging of precipitation into the model physics. Here's a nice vortex that kind of does a little roundabout there. So the rain in the center of a tornado should probably not be there, and we have to, I think there's a Blue Waters project that's focused on centrifuging tornadoes. So maybe we'll learn something from them. And then eventually it gets rain wrapped, and this goes on even longer. I'm gonna, for the sake of time, I'll stop it. But anyway, very realistic, very encouraging results. And we're seeing some very interesting things that sort of question some of the assumptions that go into tornado genesis, at least in this particular simulation. Here we're showing just vorticity shaded by the vertical component. So the red is cyclonic. This is showing you where the mesocyclone is. Here again is our updraft. We're looking at it this direction, so we're looking from like the rear flank towards the southeast. So again, here our updraft, you'll see it gets stronger. Eventually, this region sort of smooths out. It seems like it gets more laminar. The SVC, at some point, we call this is our feature we're talking about, streamlined vorticity current. It's sort of this horizontally rotating cool air that gets tilted into the mesocyclone. It does not impact the tornado itself, however. It's separate from the tornado. Here's 4 different views of that as well. Here you can really see the consolidation of the vortices here. The blue ones are anticyclonic. They behave differently than the red ones. But one thing I notice here is you start to see consolidation of cyclonic vortices, and then also this sort of sweep around. The forward flank vorticities kind of sweeping around to the rear and then getting pulled up. And right about then when you see that sort of roundabout flow is when you see the tornado form. So we've got a really good data set here, and we can go into this quantitatively and really start poking around and doing budget analyses and such. But this tells a pretty good story. Okay, so I'm going to shift gears tremendously right now and talk about compression. As you can see, I save a lot of data, and I know a lot of users on Blue Water save a lot of data. Well, I was reading the HDF mailing list a few months ago, and I saw that there's this new floating point compression algorithm that's out there. So Peter Lindstrom, I think he's at Lawrence Livermore, has developed a compression technique. It's lossy. We've begun to use it. In fact, all the stuff I've showed you so far was compressed with this technique. It's allowed us to reduce our data load by around 30 times, factor of 30. That's a big factor from lossless gzip, which is what we were using before with HDF. So the question I asked myself, and you may ask yourself as well, if you're doing double precision, do you really need all 64 bits of precision for your output, or even 32? Or what if you could save data by sort of specifying the amount of accuracy you really need? And that's what ZFP lets you do. For me, the biggest bonus is that you can basically specify the accuracy of your data in terms of the data itself. So, 0.1 kelvins or 1 dBz if you're doing reflectivity. And then the compression handles it. It's pretty easy to use. You use this module here, you initialize it, you create a property list, you turn chunking on HDF, you create your data set with this little extra argument here, and then when you write your data, it undergoes the compression. So it's pretty easy to stick in your code. Like all compression algorithms, I think, with HDF, you have to use serial HDF. I know there's efforts in getting it so you can do a parallel HDF. So all of our data is being saved on one Blue Waters node. So we're doing serial HDF in parallel, in a sense. We're saving individual files. Performance is good. There are some I/O issues I'll talk about next, but I don't think they're related to ZFP. I think there is something to do with HDF. So I'll show you this image first because I want you to compare it to the next slide. This is the reflectivity. This is like what you'd see on radar. The next slide is going to show you, instead of, you'll see nodes on the X and Y axis, and in the nodes you're going to see the compression ratios. So these are the compression ratios. So each of these represents a file. This is averaged over 180 time steps, so it's been pretty good data. So here, using 1 for accuracy, I get a mean compression ratio over the domain of about 22 to 1. You see less compression in the area where most of the action is. Pressure, I get about 30 to 1. And again, for all intents and purposes, the data looks lossless to me for most of my things I do. Cloud and microphysics variables compress extremely well, primarily because you have a lot of zeros, so any compression algorithm will do well. But still, even so, this is a very lots of accuracy, and we get a tremendous amount of compression. So that's really nice. And same goes for rain, 780 to 1. Notice the log scale. But let's be a little closer here. So this is the full domain, but since the tornado's over here, let's just look at the compression in this region. Because while this looks really good for vorticity, which has a lot of horizontal variation and hence won't compress as well, notice these pink colors really are down here. So let's zoom in on this region right here. And now we see, so this is like the next image I'll show you, about 20 to 1 in the region where most activity is. So, you know, again, you expect that. Here is that field, and here it is going to even trying to get even less. I'm trying to make it as bad as possible. I'm switching back and forth. But ZFP does a really good job. Even when you choose a value of 1, when you're ranging from -2 to 2, it still looks really well. I think it's a very conservative number, in fact. But anyway, so this is something to consider. One last thing before I go, I have been looking at performance of just buffering the data to memory, because I'm writing these files to memory before I write them to disk. And I see a large variation, not in this image. In this image, you see that, yes, it takes a little longer. It takes about 2.5 seconds in the region where most of the action is and less time here. But sometimes it takes a lot longer. I'm going to step forward in time. So I'm just tracing the amount of time it takes to write each file to memory. Okay, we're not even touching the file subsystem, or we're not talking the communication. And sometimes you get these little localized regions where it takes like 10 seconds to write instead of 1 or 2. This is something I think is related to dynamic memory allocation. It's a big guess. I don't know what this is. I have to get to the bottom of this because we'll get even better performance out of this if we can sort of nail that. And Garrett Haber and I have submitted a patch to HDF that allows you to allocate all of your memory up front and never touch it again. Maybe that'll help. So some parting thoughts. The tornado stuff is great. We've managed to sort of get a handle on this. We can do these simulations. We're going to do higher resolution simulations, but we're really getting a lot of science out of the 30-meter simulations, which again are pretty much the highest you've seen published. Using the ZFP is going to allow us to do things like save data every time step. That's going to be cool. I want to save data every time step when the tornado is doing some interesting things. Okay, so that's 7 times more data than I'm using now because my time step is about 1/7 of a second. The features I've identified, I've only just scratched the surface in this talk, but we have to go find these in nature. Future work will include sensitivity studies with other environments, Joplin, Missouri, Tuscaloosa, Alabama, Greensburg, Kansas, other big high-profile events. And we'll see if some of these things that we see are in those storms as well. And that's it. I'd be happy to answer any questions.
You had mentioned at the start that for almost exactly the same case, sometimes you produce a tornado and sometimes you don't.
Right.
Why is that happening?
I think it's like the problem Lorentz found a long time ago with sensitivity to initial conditions. Because these simulations, small changes in the initial conditions lead to large changes in the final state. It's just the nature of chaos and nonlinear equations. So, and it's kind of like the real atmosphere. You know, you'll have 2 storms on radar, both look really good, and one produces a strong tornado and one doesn't. So I think the model is sort of showing some of that natural variability that exists in the atmosphere. It's just showing it in a very model-like way in that just small changes in initial conditions lead to large changes down the road. So it seems like there's certain things that have to happen just right within the storm itself to get the tornado to do what I just showed you. And in some cases, those things don't line up and the storm sort of goes off into another space where it doesn't produce that tornado.
You're dealing with huge amounts of data. What do you do with it?
Yeah, so the way that I save data, I don't always save the full domain, so I can reduce it then. Sometimes I don't save it all the way to the top, so I reduce it then. I usually focus on the region where the mesocyclone is. But I've got 2 petabytes of nearline storage, so I compress it, I make sure I only say what I need, and I send it to nearline. Now, what happens when my Blue Waters allocation ends? I'm currently writing in like pieces of a luster cluster into every grant that I write, so by the time Blue Waters goes away, I might have like a petabyte. But seriously, it's a problem. I know there's some efforts within the Blue Waters world. They know this problem, but it's still a big problem. Where do you park your data?
I think particularly now that funding agencies are mandating archiving, right? And now there's a disconnect, I think.
Yes, between reality and you know what they want. Sure.
What you I think you asked, but what What do you use the data for? Is it just visualization, or do you do analysis?
Oh, analysis for sure. The reason why I'm doing so much visualization is right now is because it helps us to choose where we're going to do the numerical analysis. Right now, I don't, because this research sort of blew up when I was at a different school. I didn't have any grants. I don't have a team yet. So once I get the team going and the grants going, we'll have graduate students on board and we'll do more quantitative analysis. But we've basically we're going to be writing papers on this shortly. They're on the way. They're just.
Have you considered any in situ visualization or analysis to reduce the I/O?
Yes, I don't really care for in situ because I see it goes away, right? For me, I run a simulation and I've got 10 years of data. So in situ doesn't do anything for me. For me, it's all about where I can archive my data so I can spend the next few years actually pawing through it. So it's I see the value of in situ, but for my personal application, I don't see much value to it.
Susan, you want to set up while we take one more question?
Okay, I have one more question. Someone mentioned about the initial conditions, and if once you get to the point that you do form a tornado, how sensitive are the characteristics of that tornado to the initial conditions? In other words, is there a real bifurcation between either forming one or not, or is there a whole spectrum of characteristics?
Yeah, there's a spectrum. I would say that's probably the more. There's a spectrum of solutions, and we haven't done enough simulations to really find them yet. But I know there's a spectrum of simulations that does this. This isn't the only simulation that produces this, but I sometimes get short-lived EF5s. Sometimes I get anticyclonic tornadoes. I get some interesting things, but I haven't done enough runs to answer that question yet.
Time for one more, and we'll take a question.
Tracer experiments. Have you looked at that or thought about it? I mean, at least in our department, there's a lot of people looking at mixing and source region.
Using Lagrangian parcel analysis? Oh yeah, yep. We've done that already with Visit. We're actually going to go into the Visit source code and find ways to save values along trajectories so we can do Lagrangian parcel analysis, budget analysis. There's another guy at the UW who's interested who does Lagrangian parcel analysis with large numbers of parcels. So yeah, that's another avenue we are pursuing.
Okay, thank you again, Lee.
Thanks, yep.